Debye model. Okay, so the Debye model. What I want you to remind you is why we start with the Debye model, what have been done before Debye. So before Debye, there was a model for behavior of solids, basically the heat capacity of solids, which was a model that was developed by Einstein. And the Einstein model assumes the following, that we have a lot of atoms, particles. Each particle is simply located at some specific position, and it can vibrate just like a mass on a spring around this location. All the particles are exactly the same. All the spring constants or vibrational frequencies are exactly the same. And so this model was solved by Einstein very, very easily, which is quite nice. But it showed some discrepancies with the experiment. So what the main discrepancies, so what the biggest predictions of Einstein is, the low temperature behavior of CV and the high behavior and the high temperature behavior of CV. So the high temperature behavior of the heat capacity was quite similar to what is seen in experiment. So you take a solid, you measure its heat capacity. It can be actually done in a lab. And what you can see that as the temperature grows, at some point it basically saturates and becomes a constant. So the CV as a function of temperature looks like this for high enough temperatures. Now, the other point was made by Einstein is what happens at the low temperatures. So at the low temperatures, it was going to zero. Right? And in experiment also, you look on the heat capacity for low enough temperatures, you also see that it drops to zero. The problem was that Einstein model predicted an exponential behavior with the temperature. Okay? Exponential of t. And in reality, it was t to the third power, or some power of the temperature. So it's basically clearly that something is wrong with the description of Einstein of the solid for low enough temperatures. And today we actually somehow understand what is wrong, because we have a perspective of the solid which is quite different from what they had before. So we do know that's particles, but we do also understand that for low enough temperatures, the particles are not just vibrating somehow with one specific frequency. The different vibrations are correlated, and the different vibrations are connected, because each particle is affecting by its motion also the other particle. Even forget about the quantum mechanical perspective. Just take as a pure classical description of masses on springs, and that the springs are somehow, or some sort of interaction between the particles, and those interactions are relating the vibrations and the motions of all the different particles to each other. So one single particle cannot simply perform any kind of a movement which is not related to the movement of the other particles, especially for low enough temperatures. Okay? We will see that what happens actually in low enough temperatures, they all do something together. Okay? So what Debye tried to do and change in the Einstein model is basically to take the same perspective, particles described as masses on springs, but not one single particle, but actually masses on springs or vibrations are of a normal mode of the particles of the whole solid. So instead of trying to describe all of this as not connected to each other, he tried to represent it as everything as it's some sort of a connected. All the particles are connected to each other, but we can find a representation which we call the phonon representation. And in this phonon representations, the different phonons were not connected. The different modes of the vibrations of the whole solid, they were not exactly connected to each other. But, and this is the second point where the Einstein model and the Debye models are somewhat different, all the different phonons or all different modes have different frequencies. In the Einstein model, everything was the same. All the vibrational frequencies of all the particles are exactly the same. In the Debye model, there are different omegas. So we indeed can represent everything as some oscillators, as a sum of a lot of oscillators. But the frequencies of each oscillator, it can be different from everything else. Right? Why it's different? Why it's different? So again, what we are usually, we will start with the description of the Debye model from the lattice point of view. So first of all, let's write down the Hamiltonian of the Debye model, and we will look how we can make a transformation. I will just write it down from the general perspective of the solid with some general potential to a very specific description which basically describes small vibration around equilibrium points. Okay, so what is the kinetic energy is simply what? It's simply a sum of all the different particles and all the different masses. So we have a sum of I from 1 to n. N is the number of particles. A sum of alpha, which goes from 1 to 3, of mi. Okay, what is mi? This particle is number I. Its mass is mi. Okay. Alpha, it has 3 directions of motion, 3 degrees of freedom, x, y, and z. So write it down as x, I, alpha, dot, square. Okay. Now we can write down psi I alpha as xi alpha minus xi alpha 0. What is xi alpha 0? The equilibrium position of particle number I in direction alpha. Okay, so by using this representation, kinetic energy is simply I from 1 to n, alpha from 1 to 3, of mi psi I alpha dot square. Okay, because if you take the derivative of the left hand side and the right hand side, the derivatives with respect to time are equal. Great. The moment we have done this, the next step is to write the potential energy. The potential energy is simply what? It's V, or let's write it as U, potential energy. So we can write it as U0 and then expand it in a Taylor expansion. So what we will have, plus dou u du du psi I alpha, sum of I and sum of alpha, psi I alpha. Okay, so this is the first order in our expansion. We also will take the second order, I1 alpha 1 sum of I2 alpha 2 dos d squared u t d psi I1 alpha 1 psi I2 alpha 2 psi I1 alpha 1 psi I2 alpha 2. So this is the first order, this is the second order, and afterwards we had all the higher orders, right? Plus da, 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 da. So it's the third derivative of the potential, the fourth derivative of the potential, etc., etc., etc. Now, in the spirit of Einstein, we're saying, let's cut everything that's here off. We don't care about this. We take only the second order representation of our harmonic potential. So this is a quadratic form. Okay, why quadratic? Because in terms of our size, this is a polynomial, a second order polynomial, so it's called a quadratic form, and it can also always can be rewritten in a different fashion. Okay? So if we would make the following, there is always a transformation such that psi of alpha equals sum of r b I alpha r q r, and r goes from 1 to 3n. Okay, so there is always, this is something that we learn in a class of analytical mechanics. So if we have a quadratic form, we can always find a transformation from this coordinate to some other coordinates such that this form will be represented how? So u is equals to u0 plus, by the way, this term also disappears. Why? Because we are using psi's, and psi's are exactly the points of equilibrium. Basically it's taken around psi I alpha equals 0. Here psi I alpha equals 0. So we are taking the derivatives where exactly the points of equilibrium, when psi I alpha equals psi I alpha 0. At the point of equilibrium, the first derivative of the potential should be 0. The derivative of the potential is the force. At the point of the equilibrium, the sum of all the forces acting on each particle equals to 0. This term disappears. We're left only with this term. Okay. Now, using this transformation, we can write down u as equals 0 of we would write all the energy, the total energy, H, total energy, which is equal K plus U, and it will be equal to U0 plus a sum of I goes from, or R goes from 1 to 3n, of QR dot squared, plus omega r squared QR squared.
Why there is no 1 or 2 when you do the calculation?
Oh, well, here you're right. You are right, and I could also with that here.
I think the potential also time 1 or 2.
Where? Here?
Potential.
One half. Yes, you're right. I'm sorry. Oh, he's exactly right. So one half for the kinetic energy and one half because of the Taylor expansion. Okay. So we take this form and we say, well, so we have some kinetic energy, we have simple sum of oscillators, right? Simple sum of oscillators, and we have some U0. We have some U0. We don't really care about this U0, but we still have it. So if we solve this equation, so we have a sum of 3n oscillators. All the oscillators are completely uncorrelated to all the other oscillators. Okay, so what do you have done here? We have taken a problem which is very correlated. We assumed only quadratic interactions. Okay, we just kill everything else, which is a harmonic approximation of the problem, and we are capable. We are always capable to make a transformation to the normal mode representation. This is a normal mode representation. Why? Because I'm looking on all the different particles that are sitting in my system, okay? And those new particles, I can call them quasi-particles, later I will call them phonons. They're describing the vibration of what? Of my solid. But it's not a vibration of one single particle, right? It's a vibration of all the particles somehow together. And I'm claiming there are 3n different vibrations over here. Okay, so it's again, this is Einstein model, and the only difference from the Einstein model is that I have here different omega r's. So remember, in Einstein model it's 3n oscillators, but all the oscillators have exactly the same omega here. In Debye model, it's basically the same. The only thing that he's claiming, well, I have to take different omegas. I have 3n oscillators. Those 3 oscillators are non-correlated. The difference is the different frequency. Okay, so the moment we have different frequency, but there are still oscillators, I can write down the energies of the system. Okay, the eigenvalues for the energies. We know if you treat this problem in a quantum mechanical way, we know what the answer is for a single oscillator, and for 3n oscillators it's just 3n something. So the 3n numbers of different eigenvalues for the energies. So E equals what? U0 plus a sum of R from 1 to 3n of nr plus 1/2 h bar omega r, right? Each oscillator, the eigenvalue of the energy is nr, its quantum number, which is what? Nr 1, 2, 0, 1, 2, 3, etc., etc., etc. The only thing that I care about is it's an integer, right? And each oscillator now has a different omega r. Now, what I have already done, I've just said, well, let's write this E as U0 plus n goes r goes from 1 till 3n of h bar omega r plus a sum of r goes from 1 and r h bar omega r 3n. Now if we write the partition function, it should factorize exactly as in the Einstein case. Okay? What exactly we do? It's a sum. All different cases of nr. Any questions? No?
Shouldn't it be a half in the first?
Oh, here? Yeah. Thanks. I always forget the halves. Okay? And here we have E to the minus beta, and here I should have the energies. Okay? And what is my energy? My energy is u0 plus 1/2 sum of r goes from 1 till 3n h bar omega r plus r goes from 1 till 3n nr h bar omega r. I close my parenthesis. Now, I have to perform this sum over all different states of the system. What are the different states of the system? I have different nRs. So look, this guy I can take out. Okay? This guy I can take out and I don't really care about it. Why? Because it only contributes to the normalization factor. Okay? I can take this e to the minus beta u0 plus 1/2 a sum from r goes to 1 to 3n h bar omega r. I can take this out. Okay. And what I am left with is e to the minus beta a sum r goes from 1 to 3n nr h bar omega r. And here I have also a sum all states. So you see, this is a prefactor. Eventually I don't care about it. Why? Because I should normalize my z. Okay. And the only thing that I care about is this sum over here. Okay. So this is the point to which we got in the last lecture. How I rewrite it. Because now what I need to do, in an Einstein model, I managed to factorize it. So I'm going to factorize this guy, exactly as in an Einstein model, but we'll see the main difference between the Debye and the Einstein model here. So I'm forgetting about this term. I don't care about it at all, because eventually I'm taking derivatives, etc., etc. It's not going to be relevant. Okay? It's simply a shift in the energy, right? I can shift my energy from 0 to something else, so it's simply a shift in the energy, and I don't care about this prefactor. And for me, Z is now a sum all states of what? E to the minus beta, a sum from r goes from 1 to 3n, and r h bar omega r, all states here, meaning different omegas, different nRs. Alright, so how we rewrite this sum? First of all, we can say it's a sum, all states, of a multiplication, right? Here we have an exponent of a sum. An exponent of the sum is a multiplication of different exponents, of different e's. So it's a sum of nR's, right? E to the minus beta, nr h bar omega r. Okay. What I'm claiming is that I have to multiply everything. Now, but I can sum over all different nR's first. So let's take a specific nR, sum everything for this specific nR. It's uncorrelated to all the others quantum numbers, right? So the only thing that we have left is multiplication of all the different omega r's of a sum of nr from 0 to infinity e to the minus beta nr h bar omega r. So I'm changing only the different nr's. I don't know what are the different omegas are for all the different quasi-particles. Okay? And I'm first going to sum just over the different quantum numbers that are per a specific omega r. So in the Einstein model, all these multiplications was for exactly the same omega r. In Einstein model, it was multiplication, or this guy, in the Einstein model. This guy was simply a sum of nr from 0 e to the minus beta nr h bar omega r to the power of 3n. Why to the power of 3n? Because all the different omega r's were exactly the same. There were exactly some omega 0. In our case, we have 3n oscillators, but each of them has a different frequency. So it's not equals in the Debye model to this. Instead, first of all, we write that a sum of nr from 0 to infinity of e to the minus beta nr h bar omega r equals 1 over 1 minus e to the minus beta h bar omega r. So this is, we know, we've already seen it in the Einstein model. It's simple, right? But still we have a multiplication of all the different omega r's, right? Because, so we managed to perform a factorization for the partition function, right? But all the different factors has a different ingredient. This omega r is different for each of them. So z is simply a multiplication of 1 over 1 minus e minus beta h bar omega r. Okay, so you see the difference. Einstein model, which is 1 over 1 minus e to the minus beta h bar omega r to the power of 3n. Debye model, a multiplication of all different omega r's of the same factor. Okay. So this is the main difference between Debye and Einstein. So in Einstein, we basically finished, right? Because this is the final answer. In the Debye model, we need to perform this multiplication still in order to answer our question. So if we wanted to calculate the free energy, which is minus 1 over beta, a log of z, simply minus 1 over beta, log of pi over omega r of what? Of 1 over 1 minus e minus beta h bar omega r. We can forget about omega r, we should have just different omegas here. And this equals to 1 over beta, a sum of omega, a log of 1 minus e to the minus beta h bar omega. Okay. So the difference between Einstein and Debye, here I know the answer because I have already performed the sum. I can take the log of it. It's very, very simple. Here I have to sum over all different omegas, possible omegas in the system. So I already perform a summation of all different quantum numbers nr. But the omega r's, I have to define them somehow. I have to think about a mechanism where those omegas are actually coming from. Okay? Perform this sum, and only then I will have the free energy. Okay? And this is exactly where the density of states is coming into the picture. Why? Because what actually I have here? I have a sum of omega, 1 over beta, of log of 1 minus e to the minus beta h bar omega. I don't know how to perform the sum. I have actually to count. And you remember I hate counting. I like to perform integrations, but I hate counting. So what I'm doing, I'm saying this summation, I'm assuming that the density of states is, so the different omegas are dense enough. So this summation I should transform into an integration. Integration of all different omegas, which have here 1 over beta. What I'm counting, I'm performing some averaging, right? So what I'm averaging this guy. So it's log of 1 minus e to the minus beta h bar omega multiplied by the density of states of omega d omega. Okay. And this guy, we already calculated. We already know what it is. Okay, or at least we try to understand what is this d prime omega d omega. So I'm almost finished with the Debye model, or at least I got into the point where I only need to calculate the density of states of all the different omegas. Okay. And then I have to perform this integration, or if I want to calculate, for example, the average energy, I should take, there is a relation between F and the average energy. I want to calculate the heat capacity. I can also do this. I can start from this point. In any case, for all the following calculations, first I need to figure out what is d prime omega d omega. Okay. So this is the second step of the Debye model. First he follows Einstein. He has no assumptions about what are the different omegas. The moment he reaches this position, although he used different method, but the moment he reaches this position, he says, now I need to understand what is my density of states. Okay. And you remember that in the last lecture, we actually answered this question, right? So there was a specific description of what is the density of state. I will just remind you. So the density of state was that we calculated for an isotropic media, for waves in the media, that d prime omega was v to the power of 1/3? No. It was v divided by 2 pi squared k squared of omega dk omega d omega. And k of omega was our dispersion relation. So remember, we assume that we have box of L by L by L, so it's our solid, and there are some specific standing waves in this box. And there is a relation between the wave vector size, k of omega, okay, and the frequency of the waves. We assume that our boundary condition basically state what are the possible case, or what are the possible waves that are expected in this box. It's just the standing wave, or all the possible standing waves that are expected to live in this box. This gave us a specific condition. This gave us a specific condition of how to find or how to count the different numbers, right? Different numbers of the states for different possible omegas, for different possible wave vectors. And this is how we obtain this formula over here, by simply counting different states. We again there perform some sort of integration. Now, what is the dispersion relation? How k of omega how k of omega behaves, how k behaves with omega. So here Debye assumed something. How should we find the dispersion relation? So we should write the Schrödinger equation for our solid, right? Solve it in a quantum mechanical wave in the representation of Eik dot r minus I omega t. Okay. Find all the different k's, find the solution of the Schrödinger equation, and find the relation for k as a function of omega. The problem of Debye, he has no clue what Schrödinger equation is. Okay. It's far, far before the Schrödinger had written down his equation. So what Debye thinks or assumes here? He says the following thing, or this is how we understand the argument goes. Till this point, I assume something about quantum mechanics. At this point, when I want to write down what is the dispersion relation, I'm going to assume that the medium is classic elastic medium. Okay. So I have a classic medium, and in this classic medium, I have a connection between omega and k. What is the connection? Basically, I have waves, like sound waves in the material. And those sound waves in the material for small k are going linear with omega. What is the connection? Yeah. So k of omega equals 1 over c. C is the velocity of sound in this media, multiplied by omega. The thing is that in reality, even in elastic media, what starts to happen? So assuming that you will try to solve the wave equation in elastic media, and all that there is harmonic springs between different particles. You would see that the dispersion relation, it's not always linear. It actually behaves as a sinus. So k of omega goes as some sinus of omega. So even for a classic system, this relation goes something like this. Debye didn't really care about this. He said, I want to solve this hard question, but not too hard. What is he meant by not too hard? Let's assume that I always have a linear dispersion relation. Okay, so this is Debye. This is Debye. Okay. And basically, he said, I have states, relation between k and omega, which goes linearly with omega till some specific k Debye. And I have absolutely no omegas or no states for k Debyes in the other regions. This is an assumption that Debye made. He basically said, I have an elastic media, I have a perfect elastic media. Okay, I have a perfect elastic media. And I don't really care about the long or large case. Or he didn't really care about small wavelength, because k is 2 pi over lambda. Lambda is the wavelength. So here, for small case or large wavelength, this relation is basically true. And this is somehow described the motion of a lot of particles together. And when a lot of particles together, think about two particles, they tend to move together, they tend to oscillate together. this is this description here, and it is good. Here Debye said, I'm not going to describe anything. Let's forget about it. And it's also physically true. Why? Because, well, when your lambda is small enough, so your wavelength is small enough, and you're looking on the long or large wave vector numbers, large case, there is no elastic media anymore. Because you're trying to describe waves, and the length of those waves is smaller than the distance between the interparticle distance. Okay. So what is actually oscillating between the two particles? It's not a continuum media anymore. So you have distinct particles, they can oscillate. Then you can describe it something as a continuum media. But when you're trying to describe something that oscillates between the particles, it's already not true. There are no particles there. So this classical description, in any case, falls down in the small wavelength limit. But here, it might be true. So this was a guess by Debye, but it's a very, very intuitive, physically based guess. So Debye said, I'm going to use a linear dispersion relation for the case, and I'm going to use a cutoff for large omegas. Why? Well, because I can, and if it works, it's great. If it's not works, well, the whole method is not good. But if it works, in any case, I'm trying to describe the vibrations of the system of the whole. If I'm trying to describe some vibrations that happens between the particles, it's already not a continuum limit. I simply cannot do this. So what is this? This behavior? This behavior is a phonon behavior. So each mode of vibration that I'm trying to describe to you, actually summed all over different NRs for each single mode, is my quasi-particles. So my vibrations, my oscillators now, okay, they are not correlated with each other. Each of them behaves exactly as a sound wave with linear dispersion relation. I will call them quasi-particles. We already call them phonons. Okay. And the only thing that is remaining is to describe what is the different k of omega for each phonon. So we want to write k of omega for phonons. And if we mentioned phonons before, basically is this collective vibration. This is a quasi-particle. So how I write it down? Each phonon is a wave. Now for this wave, for each wave that I have, I need to solve the wave equation. Laplacian of u equals 1 over c squared del squared u t squared. What is this? This is my wave equation. This is my wave equation that I've solved in order, that I have to solve in order to obtain the dispersion relation. So it has two solutions. What are the solutions? The longitudinal solution, UL equals to AL multiplied by e to the I KL dot R minus omega t, and KL equals omega divided by CL. And also I have a transversal solution, U of t. So those are the different waves or solutions with different wave vectors that I can have in my system. So it equals u, this is u of L, this is u of t. It's a of t, e to the power I k t dot R minus omega t. And kt equals omega divided by ct. So what is the difference between the two solutions? One describes a wave that's longitudinal. So basically, it's going, the k is exactly in the direction of the propagation of the wave. Okay, so it's basically the oscillations are, the wave is propagating there, and the oscillations are like this. Right? So this is longitudinal. I have also a transversal wave. So the wave is propagating there. The oscillations are either like this or like this. So for longitudinal, I have only one direction, the direction of the propagation, or against. I don't really care, because eventually it's a standing wave. For the transversal, I always have two directions, right? Because this is one direction, and the direction of which is and the transversal direction is a plane. And I need two vectors in order to describe what are the possible vibrations in the transversal direction. So I can have only one KL, and I can have two KT, because only one longitudinal direction and two vectors that are describing this vibration and this vibration. They are orthogonal to the propagation direction. When you studied this in the class on continuum theory or wave, whatever you have studied, or how it was called, you have seen that the solution to you have two solutions. One when the curl equals to 0. The other one when the divergence is equal to 0. Okay? Each of them, divergence, sorry, not divergence. Each of them provided you a different answer. One of them provided to you the longitudinal wave. The other one provided to you the transversal wave. Okay? So one is when KL cross UL equals 0. And one that KT dot UT was 0. Okay? So this is longitudinal. This is transversal. Why I'm saying it to you? Because we have three dispersion relation. One for KL, two for KT. From elastic theory, we know that the speed of sound in the direction of propagation, so CL, is different than the speed of sound that is in the transversal direction. Why? Well, there is a claim because of the structure of the media, etc., etc., etc. But there is, in general, a difference between the longitudinal propagation speed and transversal propagation speed. That's basically it. So when I'm writing d of omega, d prime omega, okay, what I should write is v divided by 2 pi squared multiplied, so here I have k squared of k of omega dk d omega. I should have a contribution for KL, for KT, and for another KT. Okay, so we should have here KL squared of omega dKL d omega plus KT squared of omega dKT d omega plus K squared of T of omega dKT d omega. Why I sum up over all different K's? Because remember, I got this result by actually summing up of all different values of the wave vector. Different states were provided not by omega. different states were provided by the situation where I have standing wave and only specific wavelength can actually occur in the media, and this gives me different case. So I have to sum up all the case in the longitudinal case, the transversal case, and the other transversal case. 3 contributions. We'll use this guy. Okay, so what we have now? So K squared L of omega equals basically omega squared divided by CL squared. dkL of omega d omega equals to 1 over CL. Kt squared of omega equals omega squared divided by Ct squared. And dkt of omega d omega equals to 1 over Ct. Okay, now I plug in everything inside this guy. And I obtain that d prime of omega equals the volume divided by 2 pi squared. And here I have omega squared divided by CL to the power of 3 plus 2y2, because those contributions are exactly the same. Those are the 2 transversal contributions. Plus 2 omega squared divided by Ct squared, to the power of 3. This is my d prime of omega. This is the density of states for the different frequencies. I can go backwards now, plug it into my integral for the free energy, for the capacity, for the average energy. Okay? And obtain whatever the hell I want to obtain, which is the final results, the result for the Debye model. The thing is, well, there is another constriction which I have to know. What is an integral of all possible omegas of d prime omega d omega? So I'm saying for each omega that is there, I count 1. Okay? So d prime omega, so what I'm doing here, remember, this guy is basically came from what? A sum of all over omegas. This is what this integration says, that if I sum over all different omegas of what? Of 1, I get an integral of all different omegas, d prime omega d omega. But what this sum is? 3n, right. This is exactly the total number of degrees of freedom. So what we obtain, that the integral of d prime omega d omega, which is, this is basically normalization, equals 3n. What are the different omegas that we have in the system? Omegas goes from 0, if we look on the k versus omega. We already know this. This is our dispersion relation. And this is different. 0 from some specific kd, which provide us some specific omega d. So an integration for omega from 0 to some specific omega Debye gives us 3n. Now I can represent d prime omega, the density of states for different omegas, instead of using volume, instead of using those factors, CL, 2, CT, etc., 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 I can basically say, well, I'm going to use 3n. Right? Why? Because I'm saying the following. An integral from omega debye, of what? Of v divided by 2 pi squared, omega squared, 1 divided by c L to the 3, 2 divided by CT, I'm sorry, to the 3, d omega equals 3n. Okay? So it's basically what this integral is. So it's v divided by 2 pi squared. This is a constant of 1 over CL to the third plus 2 CT to the third. Okay, multiplied by 0 to omega debye of omega d omega equals v to the omega squared, thank you, v over 2 pi squared, 1 over CL to the third plus 2 CT to the third, 1/3 omega debye to the third. And this equals 3n. So, and this is important, this is really important, we can say that v over 2 pi squared multiplied by 1 over CL to the third plus 2 CT to the third. This is the common prefactor in the omega, right? All of this equals to 9n divided by omega debye to the third. And I'm going to use this thing on the right instead of this on the left. Why? Well, I prefer to think in terms of degrees of freedom and some specific constant, instead of the volume in the system and some specific other constant, which are basically provide to me the different velocities. Well, I prefer to use this number over here. Okay, so what do we do next? Well, what we know so far. So we know how to write. We know, let's summarize it. What we know so far. A, we know that z, our partition function, is a multiplication of all different omegas of a log of what? 1 divided 1 over 1 minus e to the minus beta h bar omega. We know this. We know that our free energy is minus 1 over beta of a sum of omega of log of 1 minus e to the minus beta h bar omega. Okay, we know this too. Without the minus, I think. Without the minus. We know that it equals to 1 over beta, a sum of all different omegas, of log of 1 minus e to the minus beta h bar omega d prime of omega d omega. what we know about d prime omega, we know that the d prime omega equals 9n to what? To omega Debye to the third omega squared, right? This is it. A very nice function. So if we plotted our d prime of omega, the function of omega, it grows like a parabola, okay, till some specific omega Debye, and it's 0 afterwards. Okay? So this is our density. This is what we know, and what we have left with is to compute CV. Okay. CV is dot E to dot T, which is basically D to dt, D to d beta of log of Z. Which equals to dot to dot t, d to d beta, and instead of log of z, we have a sum, okay, a sum of a log of 1 over 1 minus e minus beta h bar omega, and we sum all over different omegas over here. So this is what we need to compute. This is what we need to compute. We have 3 minutes left. I would just write down what is the exact expression for CV before I take all the integrals. Why we are computing the heat capacity? Well, because this is what can be measured in experiment. This is how we know that Einstein model is not correct for low temperatures. Okay. And we want to see what the Debye model is actually provides for us in the limit of small temperatures. Okay. So what we are getting over here, we're getting that CV equals to d to dt, sum over all different omegas. Okay. And what we have here, should take the minus sum, so it's 1 over 1 e to the minus b h bar omega, okay, multiplied by h bar omega, okay, and multiplied by, and that's it. Am I right here, or there is some other factor when I took this derivative with respect to beta? I think that I am right. And there should be, yeah, it seems to me that I am right. Here should be e to the minus beta h bar omega. Okay, so what I have done, I have just taken the derivative, I've taken the minus out. Okay, I have done one single derivative, so of the log, it gives me 1 over 1 minus e to the minus beta h bar omega. And then I took derivative of this guy, which provides me minus h bar omega, which was annihilated the other minus that I had here. Multiply e minus beta h bar omega. This equals d to dt, sum of omega And here I have h bar omega divided by e to the power beta h bar omega minus 1. Okay. And then CV equals a sum of omega. And then now I have to take the derivative of this guy over there. Okay, so this derivative is h bar omega divided by e to the power beta h bar omega minus 1 squared. Okay. Okay. Squared. And here I have a derivative of this guy, which is e to the power of beta h bar omega and h bar omega squared.
And what about the one K Boltzmann?
Right. And there is a K Boltzmann over here. Right? 1 over K Boltzmann. Yeah? Or 1 over K Boltzmann squared. What I have done here. K Boltzmann, H bar. No, it's K Boltzmann on the top. It's K Boltzmann here. Yeah. Yep. K Boltzmann. Wait a second. It's K Boltzmann beta squared. K Boltzmann beta squared. Yeah. K Boltzmann beta squared. So I have to take the derivative of this guy, and I should write this down as over K Boltzmann. So it's derivative of e to the h bar omega divided by K Boltzmann t. Here minus 1. This is easier. Okay, and this is the result. Okay, I'm fine.
Shouldn't there be a minus at the beginning?
Yeah, there was a minus, but there is additional minus because I have to take the derivative of this guy, and it provides me another minus. There are two minuses. Okay, so one minus is by taking derivative of 1 over this guy, and the other minus is 1 over this guy. So there are two minuses. Then that's fine. And what I'm getting is that CV equals h bar squared, beta squared, K Boltzmann, sum of omega, omega squared, e to the power beta h bar omega divided by e to the power beta h bar omega minus 1, all of this squared. Okay, this is a sum, and what I actually need to do is to transform this sum into an integral, and we know how we do it. It's h bar squared. What we have eventually is that CV equals to h bar squared beta squared K Boltzmann, a sum over omega squared e to the power beta h bar omega divided by e to the power of beta h bar omega minus 1 squared d prime of omega d omega. And what we are going to do now is to compute those integrals. I'll just remind you the program though. So what we managed to do, we start from a microscopic model. Solid vibrating particles, very hard to compute the interactions that are pretty hard to compute. We start to make approximations. What are those approximations? Harmonic approximation. Number 1, quadratic form with the potential. Number 2, we make a transformation. What kind of transformation? Transformation to coordinates where there are free and So as the number of degrees of freedom, we have 3n numbers of oscillators, non-interacting particles again. And then we factorize the partition function, and we are left with only some sums, integrals, or whatever in order to compute those partition functions. But the physics ended where? The physics basically for us ended the moment we managed to represent the problem as a sum of n non-interacting particles. Afterwards, there is some math. I agree with you. There is some math, and this math can be complicated sometimes, but we will see it pretty straightforward. It's a math about calculating integrals. The real problem was you start with a microscopic description and how you go from this description to a non-interacting description. And we have managed to do so for the solid in our approximation in the Debye approximation of the solid. And this would be usual problem for us. We started with a microscopic model. We will try and make a representation of this model as a sum of non-interacting particles, not regular particles, quasi-particles, because what is non-interacting here? The phonons, the different phonons, different modes. Okay? And the moment that we have this representation of particles, quasi-particles that are not interacting, well, you need to compute an integral or a sum. Usually it's an integral. It might be difficult. We will see that it's not really difficult. But this is still an integral. Okay. You already know way better than I am how to compute different integrals. Okay, so what we are going to do right now is to do this integral. This is basically what we're going to do in the next, I don't know, 15 minutes or so. So first of all, this is where we start, and our d prime of omega equals 9n divided by omega Debye to the third?
Third, yeah.
Yeah, to the third, and omega squared. Okay. This is what we have. So CV equals h bar squared beta squared k Boltzmann, an integral from 0 to omega Debye. This is also important to write over here. This is from 0 to omega Debye. Of what? Of omega squared e to the beta h bar omega divided by e to the beta h bar omega minus 1 squared and multiplied by this guy. So it's 9n omega Debye to the third omega squared d omega. This is our integral. Okay. We can write this, so CV is h bar squared k Boltzmann t squared omega Debye to the third 9n, and inside we have an integral from 0 to omega Debye of omega to the fourth power e beta h bar omega divided by e beta h bar omega minus 1 squared d omega. Let's perform a change of variables in order to make this integral look a little bit nice. So what are change of variables? We described that z, we already used this word, so t is good. So t equals h bar omega divided by k Boltzmann t. Okay, so d omega equals k Boltzmann t divided by h bar dt. Okay, so in this new representation, CV equals to what? CV, and we also would write what is omega Debye? So omega Debye is omega Debye is K Boltzmann T divided by H bar T Debye. So CV is equal to H bar squared 9n divided by K Boltzmann T squared. Instead of omega Debye, we write here K Boltzmann T divided by H bar T Debye. Okay, so this is the prefactor. And inside we have integral between 0 and T Debye. Okay.
Omega Debye is in the power of 3, right?
In the power of 3. Yes, yes, thank you. Power of 3. So here we have omega. And omega is K Boltzmann T divided by H bar to the power of 4. E to the H bar divided by K Boltzmann T. So beta H bar omega, this is just simply T. E to the T divided by E to the T minus 1 squared. Right, this is why it's a little bit easier. And here I have K Boltzmann T divided by H bar dt. All of this equals to, so 9n I keep. What else I can get rid of is 9n kb T Debye integral between 0 and T Debye. And here I have T to the 4 E to the T divided by E to the T minus 1 squared dt. Nothing more and nothing less. Now I can have two limits. Okay, so in general I cannot solve this integral. The representation is in terms of some crazy function, but I don't really care. What I want to do is to solve two limits. One, as in Einstein model, one is the limit of high temperatures, the other limit of the low temperatures. Okay, so let's look on what happens to this integral in those two limits. Yeah.
Maybe it's t to the third.
T to the third here. Yes. T to the third, T divided to the third. Yes. Yes, you're right. Thank you. So first, let's take the limit of high temperatures. The limit of high temperatures. So what we know is T goes to infinity. K Boltzmann T is much larger than H bar omega Debye. Then, then T Debye is much smaller than 1. Because I reminded you what is T Debye? T Debye is H bar omega Debye divided by K Boltzmann T. Okay, so we need to take this integral over here, this guy, when t Debye is small, that it's integral from 0 to something small of this guy over here. So we basically want to expand the function here around what? Around t equals 0. So t to the power of 4 e to the t divided by e to the t minus 1 squared, how it goes as t goes to 0. Okay, so e to the t goes as 1 plus t. We don't want to take 1 plus t, we should take only as 1. Here it stays t to the 4. So it's t to the 4 multiplied by 1 divided by, so let's take the linear representation of e to the t. So it's 1 plus t minus 1 a second order. Okay, so this equals to t squared. Okay. So CV equals to what? To 9 n kb divided by t Debye, an integral from 0 to t Debye of what? T squared dt. So CV equals 9 n k Boltzmann t Debye to the third here, right? To the third. T Debye to the third multiplied by 1/3 t Debye to the third. This equals, this is temperature goes to infinity, this equals to 3 n k Boltzmann. CV equals 3 n k Boltzmann. If you look back on the Einstein model, this is also exactly what we had. Exactly the same result appeared in Einstein model. What it means? It means that the heat capacity is combined from 3n multiplied by kb, and we can look on this from the perspective that we have 3n degrees of freedom, and each degree of freedom contributes k Boltzmann joules, or joules divided by the temperature, but k Boltzmann to the heat capacity. They are completely uncorrelated. This was an assumption of Einstein. Einstein said, we have 3n degrees of freedom, each of them provides me some specific number for the heat capacity, and that's it. Okay, so this is the Einstein assumption. All the particles are not correlated with each other, they have some common omega, and they just wiggle around somehow. The Debye model says, well, you have some associative vibrations, so the vibrations not of the single particles but different modes. But in the high temperature limit, it doesn't matter. So each mode is basically a vibration of one single particle. Okay? It's exactly the same. The only thing that you care about is the number of the degrees of freedom. They're not interacting with each other for high temperatures, and we can assume this because in solid, this can vibrate in this form, and the other one can vibrate in some other form, and they basically uncorrelated, high enough temperatures. Great, so the Debye model, at least for the high enough temperatures, provides us with the result of Einstein, and we already know that this result is correct from the experiment. Okay? So the easy part we have done well. The hard part is the part of the low temperatures we have to find out now. So we are going to the limit of the high temperatures. The limit of low temperatures. So what we have we have that K Boltzmann T is much, much smaller than H bar divided by omega Debye. T Debye is much, much larger than 1. So CV divided by 9n K Boltzmann divided by T Debye to the third integral from 0 to T Debye of what? Of t to the fourth e to the t divided by 1 e to the t minus 1 to the second power dt equals or goes to what? To 9n k Boltzmann divided by t Debye to the third, an integral from 0 to infinity, because t Debye is something very, very, very large, of t to the fourth e to the t divided by e to the t minus 1 squared dt. Okay. What is this number over here? We can compute it, or we actually don't really care if we can compute it. Why? Because it's a number. Okay, so, what we have obtained? We have that an integral from 0 to infinity, t to the 4, e to the t, e to the t minus 1 squared dt, it just equals to some c tilde. It's a constant. It does not depend on the temperature in the first order. It does not depend on anything. It's a result of an integral which is related to the Riemann zeta function. It's a constant. We will show what exactly this constant is. But for us, it's a constant. Okay. So what we have obtained? We have obtained that CV equals to C tilde, which is a constant, 9n K Debye, K Boltzmann, divided by T Debye to the third. But T Debye to the third, T Debye is proportional to 1 over T. Okay? So, all of this goes as T to the third. Okay, so what we have found that CV goes to, as some constant A, multiplied by T to the third for small temperatures. Okay? So this is T goes to infinity. This is T goes to 0. What we have seen is that if we plot now the heat capacity as a function of the temperature, it behaves quite similarly to what we have seen in the Einstein model. So there is some constant for large temperatures and decays to 0. And decays to 0 for small enough temperatures. This is 3n K Boltzmann, which is similar for Einstein and Debye. What is much more important, that Debye predicted what exactly have been measured in the experiment. That it's proportional to T to the third for low temperatures. And this is what we measured in experiment. So our understanding, or at least Debye understanding of what's going on in the solid itself is true. It's not only makes a good prediction for some specific part of the parameters, it actually predicts pretty well all the spectrum of the temperature. Moreover, this constant A, we can compute it exact. We can compute the prefactor. We know what is 9n kb. We know what is T Debye is, right? It's just h bar, k Boltzmann, and T Debye and T Debye. So we know everything. We can go backwards and maybe associate it with the speed of the sound in the solid, etc., etc. But for us, we now, because we started from a microscopical model, and we obtain a macroscopical observation, prediction, okay, we can relate our understanding of the microscopic to what actually happens inside the solid. We know that the particles vibrate, that they somehow interact, and eventually there are phonones that are living inside the solid, and those phonones do not interact with each other. Okay. And there are macroscopical vibrations for low enough temperatures. For high enough temperatures, any particle is doing whatever. For low enough temperatures, there is a collective motion. Collective. There are particles or there are waves inside the solid that are contributed not by one single particle. Not one single particle doing something like this. 2, 3, 4. All the particles in the solid doing something together. There are waves that are combined for motion from all the particles. Some contribute more, some contribute less. But those are the normal modes. And now, as we understand, well, because we've been told and taught like this from the beginning, from high school already, and in the basic classes in physics, is that for low enough temperatures, everything is moving together. They're freeze and they're doing something together with their neighbors. This is exactly the Debye understanding, and this is exactly why we have a parallel behavior here instead of exponential. Okay. So this is nice. Right? We started with a microscopic something. We can compare. We obtain a macroscopic description. This description is actually following what is measured in the experiment. Everything worked great, and it's way better than the thermodynamics, because in thermodynamics we never started from something microscopical, maybe only for the ideal gas. Usually we started with something. Let's assume that the behavior is very general, and it's continuum, and it's such and such. Here we had particles, interactions. Everything is very well defined. Okay, now. The moment we have done this problem, we can actually go and solve huge class of other different problems that are similar to this one. Well, the system is quite different, but the technique and the approach is similar. Why? Because what do we care here about this solid, this is a rock or whatever? The only thing that we cared here is that, well, we can represent the different energies as uncorrelated, and different particles or quasi-particles as uncorrelated. So if we take some other system that have waves inside, and those waves, we can make them as uncorrelated, okay? The technique and the approach for this system will be exactly as the Debye model for the solids, right? So it's not that we just solved one simple system for the solid. We basically developed here and used an approach of statistical physics that can take a complex situation, transform it into a non-interacting system, and for this system, if we assume that this system is combined from waves, non-interacting waves, this is the way to treat it. And in order to make it more clear to you, I'm going to use exactly this approach in order to describe another problem that was the end of the 19th century, the beginning of the 20th century, which is the Blackbody radiation. Have you heard about Blackbody radiation? Yep. Usually, Blackbody radiation. Usually, this example is presented in the class on modern physics. I don't know if actually the integrals and all the approach is explained, but it's a very nice example. Why it's called Blackbody. So what is this Blackbody? So have a box. And this box, or the walls of the box, are considered black. Why they are black? Well, they absorb all the radiation, light, or whatever, that actually comes into interaction with the wall. So think about as a radiation as a kind of a photon. The photon hits the wall, and it's generally absorbed. So nothing is getting reflected. Everything is absorbed. After some time, the wall have absorbed the photon, eventually it will get some photon out. Okay, so it's absorbed photons, but it also exports photons. It's not reflecting photon, but it's what is the English phrase for this? Emitting, right? Thank you. So it's emitting photons. We're emitting radiation. So it's absorbed radiation and it's emitting radiation. And all the radiation that it hits the wall, it's get absorbed, and after a while, something it's get emitted. So we have eventually some sort of an equilibrium between the radiation inside here. So we have photons that are, I plot them as particles, but they are different waves of radiation. Okay. They are completely not interacting with each other, okay? But they are interacting with the walls, and the walls have some specific temperature T. So the radiation that is emitted from the walls of the box, okay, is reflecting what? The temperature of the wall. So in the blackbody radiation, there is an equilibration process. Equilibration between what? Between the photons inside the box, okay, and that are absorbed, and the photons are emitted. Because at some point, at time, all the photons that are now absorbed and emitted were previously emitted by the wall. So everything that gets out, exactly the same thing, get in, and again, and again, and again. So a photon gets absorbed, and then it's getting emitted, and then it's again absorbed, and then again emitted. Okay, so all the photons are in equilibrium with each other, but they don't interact with, and we don't care. But they also in equilibrium with the walls. Okay, so this is why it's called black body, because every photon gets absorbed and eventually is getting emitted. Now, why it's important? It's important because if we now getting, observing light that came to us from a specific object, we can relate the spectrum of the light, the frequency of the light, to the temperature of the object. Okay? So I'm now looking on a star, and I want to assume that this star is behaving somehow like a black body. So all the radiation that's getting emitted was in some sort of an equilibrium with the star itself. Then I can, when I'm looking on the star or on the light, and I'm looking on the frequencies, different frequencies of the light, what I can understand is what was the temperature of the star based on the assumption that this specific emitted radiation was in equilibrium with the star. Or for example, so by looking on the light and the color of the light, which is basically the frequency, I can make an assumption or prediction about the temperature. So this is why it's important. Moreover, maybe at the end of this lecture or the next one, I will also describe to you that there is a relation between something that is called universal background radiation, okay, something which is related to the Big Bang theory, and blackbody radiation. So the most precise process, I think, in nature that can be approximated by a blackbody radiation is actually this background radiation, universal background radiation. that is getting absorbed from everywhere. We'll discuss it later. It's related to Big Bang and recombination theory. But for starters, all those cool problems about light, its spectrum, etc., very simple problem. You have a body, it's black because it absorbs everything, and you have radiation inside. So particles, photons, waves that are living inside, and they are in equilibrium with the boundaries of the body. What is the relation, or what is the spectrum, for example, energetic spectrum of the light, of the radiation inside this inside this box? What the heat capacity of this light inside here? We can compute it. Why? The particles are not interacting, so if we write the partition function, it factorizes. This is A. B, the particles, or each particle, can be represented as a wave. And we know what is the density of states for the waves, right? We know this. We know that d prime of omega equals to v, the volume that the waves actually live in there, divided by 2 pi squared, multiplied by k squared of omega, dk d omega. Okay, so we know that the partition function factorizes A, and we know how to find this exact representation of the density of the state. Okay, so it's easy to solve this problem and obtain whatever we want. So let's start. How much time do we have? 40 minutes. So what I'm assuming here? I'm assuming that each particle is a photon that is living inside this box. So I have n particles. I have n particles. Each particle, En, energy of each particle. It's some specific quantas. N is an integer here, h bar omega. Very similar to what we had for the Debye model. Okay. Z, if what? Here we have omega n, because each of them has its own distinctive frequency. So there's a lot of photons, but each photon is different, can be different from all the other photons. It can have its own frequency, right? So Z of omega is the sum over all states of what? Of E to the minus sum of nr h bar omega r. Beta, thank you. Okay. And this is again a multiplication of all different omega r's, right? A sum of n e to the minus beta n h bar omega. This is exactly what we have done in the Debye model. We had different nr's, we had different omega r's. We managed to transform it into a multiplication of summations. So it's multiplication over all different omegas of what? Of 1 over 1 minus e to the minus beta h bar omega. So this transition from here to here is exactly the same as we have done it in the Debye model. So this is why I have done it very, very short. But it's exactly the same model like for the Debye, at least when we count different n's. We have a lot of particles, n particles. Each particle have its quantum numbers, quantum number of the energy, okay, and it has its own representative omega r. Okay. So we have this guy. We have this guy. And if you want to compute something like the average energy, okay, so what we want to compute? We want to compute the average energy, for example. What the average energy of this gas of photons inside the black body. So E average minus d log of z to d beta. Okay. So it's a sum of d to d beta over a sum instead of a multiplication. Sum of what? Of all different omegas of, and what we have here, a log of 1 minus e to the minus beta h bar omega. And that's it. Yeah. I haven't forgot anything here? No, it looks like it's correct. So E average equals to a sum over omega 1 over 1 minus E to the minus beta h bar omega what I have here still. I have h bar omega e to the minus beta h bar omega. Am I right?
And the minus?
Minus, I have a minus here. Yes. I have a minus. I don't have anything else. Why do I have a minus?
Maybe there was a minus.
There wasn't minus in the beginning? There was a minus in the beginning. There for sure was a minus in the beginning. There is a minus from this guy, right? So there is an additional minus. So, okay, so what we have here. So the first, we take a derivative, so it's 1 over 1 minus e to the minus beta h bar omega. Then we take a derivative of what's inside, so A, there is a first minus of minus beta, and there is an additional minus for minus over here, and in total, the two minuses annihilate. So this is the right answer, without the minuses. Okay. So one minus came from here, and the other minus came from here. Okay, great. Now, this we're going to transform into what? We're going to transform into an integral over omega of e to the minus beta h bar omega divided by e to the minus beta h bar omega h bar omega d prime of omega d omega. The thing here is what omega is. Omega can go from 0 to basically infinity. If beforehand we had some limitations because there are some specific degrees of freedom, here we don't have any limitation on the oscillations of the radiation inside this black body. So the integral is from 0 to infinity. What is the next step? The next step is to determine what is d prime of omega. So you see, it's already very easy because we have done it once. To apply the same approach to a different problem is basically, well, you need to first reformulate the problem in terms of particles, non-interacting particles, and d prime of omega. The moment you're done, you're left only with long integrals of this form. Well, what is d prime of omega? d prime of omega is d prime of omega is v divided by 2 pi squared k squared of omega dk d omega. Now this is a radiation. What we assume for radiation, k equals omega divided by c. That's it. Those are just simple waves. Simple waves. There is nothing of particles, interactions, some elastic approximation. No. Those are real waves. But again, as in a Debye model, there is something about this wave. So the wave is propagating from this direction there. What can happen to an electromagnetic radiation? Can it have a longitudinal part? No. So the wave, radiational wave, or electromagnetic wave, if it's propagated in this direction, it does not oscillate here. Okay? So if the wave is propagating in this direction, it can also have transversal part. It comes from the Maxwell equation. So it can, if it's propagating there, it can have oscillations in this direction and in this direction. Oscillations of the magnetic field and electric field. Okay, so propagation is there. If there is a propagation, there is only oscillations in the transversal directions. Okay, so there is kt, which is omega divided by c. And there are two of them. So d prime of omega equals v divided by 2 pi squared of omega squared divided by c squared 1 over c plus omega squared divided by c squared multiplied by 1 over c. C is the velocity in this specific media that's inside the black body. If it's a vacuum, so C, it's basically the speed of light. Okay. So let's write down our average energy. So the average energy is an integral between 0 to infinity of e to the minus beta h bar omega divided e to the minus beta h bar omega. And here we have v divided by 2 pi squared multiplied by 2 divided by c to the third power multiplied by omega squared. And d omega over all of this.
The 1 minus the...
Ah, yes, thank you. So here what I had, 1 minus e to the minus beta h bar omega. 1 minus. Thank you. Okay, so let's take everything that we can out. Let's make the following. E is our energy, okay, per oscillator or per n. So we'll make this as E equals h bar omega. Okay, so d omega equals d epsilon 2d to h bar. Okay, and now we simply get it inside. So E average equals 0 to infinity e to the minus energy divided by k Boltzmann t h bar omega which is basically epsilon v divided by pi squared c to the third. Instead of omega we have epsilon divided by h bar squared. And here we have 1 minus e to the minus e divided by k Boltzmann t. All of this multiplied by d e divided by h bar. Okay, let's rewrite this as an integral from 0 to infinity of e multiplied by everything else. What is everything else? So I have here v divided by pi squared c to the third h bar to the third epsilon e squared e to the minus e k Boltzmann t divided by 1 minus e to the power e epsilon k Boltzmann t dE. Yes. Yes, I can actually do. I can rewrite this as multiplied by 1 e to the epsilon k Boltzmann t minus 1. Okay. So what we obtained the average energy. The average energy equals to energy per state multiplied by something, integral over all possible energies. So if I want to compute the average energy, what I want to do, if I want to compute the average energy? It's an integral from 0 to infinity over the different values of the energy, okay, multiplied by the density of states for the energy, Okay? This is the averaging procedure, right? If I have what is the average E, is E multiplied by the probability density function of E dE. This is the definition of an average procedure. So what we have here? We have here that the probability of density of states, the PDF of different energies, is simply V divided by pi squared C h bar to the third power epsilon squared divided by E epsilon k Boltzmann t minus 1. Okay, we can say it's just E d of E d of E. So we have here E, E, and E. So this is the energetic spectrum of a Blackbody radiation. You want to plot it, for example, to see how it looks? It's very distinctive. Okay, so d of E as E, what we have here, for very small e, it behaves as what? It behaves as E. It grows linearly, and it has a maxima, and then it decays. This is how this energetic spectrum, or the frequency spectrum, which is very much related to this, looks like for blackbody radiation. Now, what we can do from here is actually, for example, look on the radiation of a star and see if it looks like this, and it's pretty close. It's not that far away from this plot. We can look on the radiation of something which is called whole round. So, for example, you take a closed body, which is not exactly black, but very close to the black one, and then you send a small number of photons inside it. The photons are getting absorbed, emitted, and then you calculate actually, calculate or you observe what is the spectrum of the radiation that is inside, and it looks like this, pretty much close to this. An interesting observation was made in the 60s, I think it was in the 64, but Penzas and Wilson. So they were using radio telescopes in order to detect some specific radiation that is coming from stars. And what they have seen that no matter where they were pointing their telescope, radio telescope, they were getting always the same background signal. Always. It was not dependent on the time of the year, on the direction, on anything. So their first guess where this signal is coming from was, well, there are pigeons sitting on the antenna and doing something to the antenna, and this is the noise they were getting. They get rid from the pigeons, but the noise was still there. And eventually what they understood and predicted, that the signal that had this specific distinctive shape, so the frequency, so the distribution of the different energies of the signal was exactly this, exactly as a clear experiment can be. So if you plot a border, an error bars on their experiments, there is basically none. It's very exact. They managed to relate this signal to the Big Bang theory. So, and they basically, what they have been measured for the first time in the 1964 is the cosmic background radiation, which is some radiation that has been still there and still around us from the Big Bang. So the Big Bang theory states the following. So there was nothing and there was something, and this something expanded really fast. There was a huge expansion that appeared as that the universe grew enormously fast on time scales of 10 to the minus 70 or something, or 31. And there was plasma. Plasma of hydrogen atoms. Okay, so there was electrons and protons. Everything was ionized. Okay, and there was also radiation. And there was an interaction between the electrons, protons, and the photons and the radiation. But still the universe continued to expand. Now this interaction between the ions, hydrogen ions, okay, they were still not hydrogen, but were hydrogen ions, and the photons was some sort of a blackbody radiation. Why? Because all the photons, they've been obtained from this energy, from this plasma, and they interacted with this plasma. So all the photons that were there at that time are only photons that got absorbed and emitted by the plasma. Now the universe expanded, and at some point it became cooler, like a gas. You take a gas, you make it expand, all right? and then temperature drops. Temperature started to drop, and this plasma, instead of being ionized hydrogen, just became hydrogen. Okay. The moment it became hydrogen, the photons, or some of the photons that were still around, could not interact with this because of the difference in the energy levels, right? So there are photons with specific energies. There are hydrogen with different energy spacing. Those photons cannot be absorbed by the surrounding, and they are still there. Okay? The temperature is decreasing, right? Because the universe is still expanding, but this radiation should be there. According to the Big Bang theory, this cosmic background radiation should be anywhere around us, because there is no plasma left, or almost no plasma left, that could absorb and emit those photons. Okay? So you get the specific signal from anywhere in the universe, and it's a reminiscent of the early stages of our universe that was like billions and billions years ago. Okay? And when you take this prediction that it was a blackbody radiation, and you measure the spectrum, the energetic spectrum that you obtained from the prediction for blackbody radiation, it shows an exact, almost, not almost exact, but a very, very exact behavior, exactly as it was predicted by the blackbody radiation. So it's just fantastic. So if any of you have performed measurements in the lab here, back in your homeland, well, there are always error bars. So I'm an awful experimentalist. So my error bars were always huge. Now you look on the papers about the cosmic background radiation, and you look on the error bars, they are smaller than the width of the line and the figure. Like it's enormously precise. So it's very cool. It's very cool that you can take some very simple physics, solve it, and accordingly to observe something in nature. Now, so this is our prediction for the blackbody radiation. Now, back in the end of the 19th century, they knew nothing about background cosmic radiation whatsoever, but they could measure the temperature dependence of emitting bodies. Okay, so they have a body, it's emitting, or you can look at, you can take a small, make a small hole in some specific body, and you observe on the radiation that comes out from this hole, and you can observe what is the behavior of the average energy of the radiation that's coming out. So we can actually not only say, well, this is the distribution, but we can actually solve this. Okay? We can actually solve what is average E. The integral from 0 to infinity, E V divided by pi squared, C H bar to the third, epsilon squared, E epsilon K Boltzmann T minus 1 yes. Okay, so now let's take out all the constant. So we have V over pi squared, C H bar to the third. Here we have an integral from 0 to infinity of epsilon to the third, E epsilon divided by K Boltzmann T minus 1 d epsilon. Now we are almost there. We're almost there. The only thing that bothers me that I have epsilon here and I have epsilon divided by K Boltzmann T over here. So let's change our variables again. Let's change our variables again, and let's say that epsilon divided by K Boltzmann T equals to x. Okay? So d epsilon equals K Boltzmann T dx. So we have average energy equals to volume by pi squared C H bar to the third of an integral between 0 and infinity. Instead of epsilon, we're writing K Boltzmann T to the third x to the third, right? Divided by ex minus 1. And here we have k Boltzmann t dx. And E equals v divided by pi c h bar to the third, k Boltzmann t to the third, k Boltzmann t. Fourth, we have here k Boltzmann to the fourth, t to the fourth, an integral between 0 and infinity of x to the third, e of x minus 1 dx. Now this integral is, well, maybe we will make it later, so I'll just tell you what it is. So an integral of 1 over n x to the n between 0 and infinity divided by ex minus 1 dx equals to zeta of n plus 1. And this is Riemann z zeta function. Okay. And now its values are known. So in our case, an integral of between 0 to infinity of x to the third of e to the x minus 1 dx equals to 3 factorial of zeta of 4 equals pi squared divided by 15. Okay, you can compute this exactly. It's not pi squared, pi to the fourth divided by 15. Okay, so the average energy is equals to V divided by pi C h bar to the third K Boltzmann to the fourth T to the fourth multiplied by pi to the fourth divided by 15. And we have E average equals to pi divided by C h bar to the third K Boltzmann to the fourth T to the fourth multiplied by V. And this is a very known Stefan Boltzmann law. So the average energy of a black body grows as T to the fourth. So again, the technique is known. The only thing that was left here was just computation of the integrals. So we are done for this part today. Hopefully what we start to do next lecture is actually how we're going to see how we are using this representation of non-interacting particles for different quantum statistics like Bose statistics and Fermi statistics. Bose statistics, particles do not interact, but in Fermi statistics, there's some sort of interaction. How we do use those representations in order to use this application of non-interacting particles. And we also are going to present, instead of canonical ensemble, a macrocanonical ensemble. So hopefully all of this next week. Thank you.